Hello, geometers, and welcome to the lesson on proportionality theorems. And what we've talked about before in this chapter are proportions of different triangles. What we will discuss today is proportions in the same triangles or proportions, outside of a triangle. Right. So the goal today is for you to be able to solve and identify proportions that don't exist in two different triangles or that aren't in a triangle at all to begin with. So let's go through these theorems, and they're pretty intuitive once we make sense of what the words are saying. So let's go look at the first one. If a line parallel to one side of a triangle intersects the other two sides, then it divides the other two sides proportionally. Okay? So let's say I have a triangle, and let's say this is just named ABC. I have a triangle, a line parallel to one side of the triangle. So it doesn't really matter where this line is drawn as long as it's parallel to one side. So it's this line here is parallel to AC, and it intersects the other two sides. So I should call these points of intersections D and E. Then it divides the two sides proportionally. Now this phrase here is a little bit ambiguous, but we can think of it in a little bit more precise terms using the picture. So what this is saying is that if you compare the segments on the same side of the triangle, so DB over DA, then that is equal to BE or EB over EC. And notice that here that this proportion doesn't involve two different triangles. It's just the same one, but it involves segments on within the same triangle, as long as you have this line here that's parallel to it. We'll prove this later so you can see why this is true, but for now, let's learn the theorems. Let's apply them, and then we'll deal with the proofs of them later. Okay. And then next we have the converse of that statement. So if a line divides two sides proportionally, then it is parallel to the third side. So this is saying just the opposite, or the converse, that if you have ABC, and this time you don't know ahead of time if it's parallel or not, but you have some other line that cuts through. Okay. And notice here, I'm very careful not to say that this is parallel. And if this proportion is true, then we can say that the lines are parallel. Then DE is parallel to AC. Okay. So the first part of the theorem says that if we know the lines are parallel, then the proportions are equal. The second part of the theorem says if we know the proportions are equal, then the line must be parallel. So just moving along, if three parallel lines intersect two transversals, so let's see, let me give three parallel lines here, here, and here. Okay. These three lines are parallel to each other, and then I throw in a couple transversals. Okay, so the blue lines here are our transversals. So this is similar to what we had earlier with two parallel lines and one transversal. And I'm going to name these points A, B, C, D, E, F. Okay. So what this theorem says is that if you have this situation, then there is a proportionality that exists within these particular blue segments. So if we were to compare AB and BC, that would be exactly equal to DE and EF. Okay, that's what this theorem says. I'll give you a hint as to how this proof is going to work. basically, if we were to extend these lines here, we would make a triangle, and we can do some nice things with the similarity of that triangle. But we'll worry about proofs of this later on. We'll just right now want to understand the theorems and then later use them in some helpful way. Okay. So the last theorem we're dealing with today, bisected angle proportionality. If a ray bisects an angle, and bisects means to divide exactly in half, then the opposite side, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So say I have some triangle, and this doesn't have to be any special type, okay, just any regular triangle, and then I have a ray, let's say this is ABC, an array that goes through here and cuts this angle in half. Okay, that's what it means to bisect, and I would name this point here E. Okay. Then what we can conclude is AB over AE. So looking at this length and this length, that is equal to BC over EC. So 3 theorems, I have 4 listed here, but these 2 are basically saying the same thing, just with slightly different conditions and conclusions. And then a statement about 3 parallel lines and 2 transversals, and then a statement about angles in a triangle being bisected. And that was a lot, and we can get this mixed up easily. So I'm going to pause. I'm going to end this video here, and make sure you watch the next one where I look at some examples of this with you. Thank you for watching. Have a wonderful day.